Hi, this is Owen Astrachan with Video V Compression for CompSci 201, Academic Year 2021-2022. V is for virtual memory, when 4 gigabytes becomes the cloud, essentially an infinite amount of memory because of how software is written today. V is also for a viral video. I suggest that this URL might take you to a premium example of a viral video, bit.ly/201A, how to get an A in CompSci 201. V is also for variable. Variables in Java are pointers or primitives. In this video, we're going to talk about lossy and lossless compression. For example, the RAW format taken by many digital cameras captures all the pixel data that there is in an image. And because cameras, especially digital cameras, have such a high degree of resolution, RAW format results in huge files. But image files and photographs are often stored in a JPEG format, which is much smaller because information is thrown away when a JPEG format is created. And JPEG images are easier to transmit over the internet because they're smaller than RAW format. But photographers often prefer the RAW format because it allows you to do more processing digitally of the entire photographic image. Often, when you're storing information in the cloud, in a service such as Dropbox, Box, or Google Drive, you may compress or zip up an entire folder full of files to be able to transmit it as a single entity. Now, that zip format, which does compress the data in a file or in a folder, is a lossless compression format, meaning that when you decompress a zip file, you want to get back exactly what you compressed. You don't want to write an essay, for example, put it in your English folder, zip it up, and then get back an essay that isn't exactly what you wrote because some information was thrown away. That's lossless compression, when you compress and decompress and get back exactly the same data. One of the first examples of a lossless compression format was the MP3 audio format. When this was created and put into widespread use as part of Napster in 1999, it led to the streaming services that we see today with Spotify or Amazon Music or Apple Music, for example, which use compressed audio to make it easier to transmit audio files over the internet. MP3s are also a lossy compression format, meaning some information is thrown away. But typically the human ear isn't able to discern that information when it's thrown away, and so we listen to compressed audio and think that it's pretty good. There's a long history of lossless compression algorithms where you get back exactly the same information. Huffman coding, for example, was invented a long time ago, and it is the optimal per character compression format. We cannot do better. It's provably the best if you look at one character or a block that's the same size throughout the file being compressed. And that will be the last project we do, for example, in CompSci 201. There are other compression algorithms that do better by considering different block sizes or the context in which certain characters occur. LZW is one such format. Many of these formats use Huffman at the last stage of compression to send blocks over the internet where it's easier to send blocks that are the same size. When data files increase in size, we typically need new lossy compression algorithms. Because streaming is so ubiquitous these days to send video over the internet, and because people want to see that video on very high resolution screens, and because streaming is used much more broadly than it used to be, new lossy compression algorithms are being developed, as well as new techniques for sending those compressed video files over the internet. Here's a quick review of how storage of data is done before compression, and it will help us understand how compression works. For example, text files use ASCII or Unicode to store information, whether that information is a letter such as A or a character in another alphabet such as the Cyrillic or Kanji alphabet. Previously, ASCII, the American Standard Code for Information Interchange, was used, which is an 8-bit per character encoding scheme. Because alphabets are larger, because more data is stored internationally, today Unicode is used, which is 16 bits per character. With 8 bits per character, we can only represent 2 to the 8th different characters. And we can see here that A, for example, the character A is represented by 65, that's in base 10, and Z is represented as 90, whereas the lowercase z is represented as 122. Now that's information is actually stored in binary, so we can see that A is 01, 000001, and Z has its own format, the equivalent of 90 in binary. Again, ASCII is 8-bit, Unicode is 16-bit. By storing information in those same chunks, it makes it easier to read. But you might consider that since there are fewer Z's, for example, perhaps we could encode Z with fewer bits and save some storage. E, which occurs more often, might have more bits to represent it. So you have varying numbers of bits per character. That was the case, for example, in Morse code, where frequently occurring characters were stored with fewer dots and dashes than characters that occurred less frequently. And that made it possible to transmit data with dots and dashes more efficiently. However, today, computers store information in uniform sized chunks, 8 bits for ASCII and 16 bits for Unicode. What we're going to do to compress is leverage redundancy. So for example, if we have a file with 1,000 A's and only 24 Z's, we might use fewer bits to represent the Z's because there are fewer of them. And then we could use more bits to represent the A, but still save bits in total. And we could switch that if we had a snoozing file that consisted of all Z's. In Huffman coding, for example, we will leverage that redundancy, but we treat all A's the same. So once we decide that an A will be encoded, for example, with 4 bits, because we're compressing, then all A's will be encoded with the same 4 bits. It's possible that we might be able to take context into account and encode the first A's with a different number of bits or a different bit sequence than the later A's. Huffman doesn't do that. And it is, as I previously mentioned, the optimal per character compression scheme. We can't compress without redundancy. We need more A's than Z's, for example. Truly random data can't be compressed when we're doing lossless compression. If we're going to throw information away, we can compress almost anything. But this is a counting argument proof that we can't compress everything. For example, if we had 3 bits per character, we'd have 8 different values, and you can see them on the slide here: 000, 001, 010, 011, 100, 101, 110, and 111. That's 8 different values with 3 bits. 2 to the 3rd is 8. With n bits, we can represent 2 to the nth different values. So for example, if n is 10, 2 to the 10th is 1024. So we have 1024 different 10-bit files. There are actually 1024 different 10-bit sequences. If we could compress them all with lossless compression so that we could get them back, we'd have to have 1024 files, all with fewer than 10 bits, because otherwise we wouldn't compress them all. So we're assuming we could compress them all, but we can't because there are 2 1-bit files, 0 and 1. There are 4 2-bit files, 00, 01, 10, and 11. There are 512 9-bit files because 2 to the 9th is 512. Now if we add up all these powers of 2, 1 plus 2 plus 4 plus 8 plus 16 plus 32, 64, 128, 256, 512, we get 1 less than the next power of 2 because the sum of powers of 2 is 1 less than the next power. So if we add up all these files of 1, 2, 4, 8 up to 512 bits, we'll get 1023 different files. That's the next power of 2 minus 1. We can't compress 1024 10-bit files into 1023 fewer than 10-bit files. It's not possible. So we can't compress every file with lossless compression. This proof suffices to show that. When we are reading a text file, as I mentioned earlier, we typically read it in 8 or 16-bit chunks because of ASCII or Unicode. Even if we're reading a JPEG file or an MP3 file, which doesn't consist of text, but rather bits, it's still read in a series of chunks because it's more efficient for the computer to do that. When we are reading a JPEG or a PNG or a GIF file, for example, the suffix might dictate how those images are displayed, so that if you load a PNG file, it might be viewed by a program that understands how to render PNG files. Or if you try to visualize an MP3 file, it won't really be possible since that's meant to be heard by audio rather than seen visually. Ultimately, however, it's the contents of the file that determine what's in the file, not the suffix. The operating system may use the suffix, but if the contents of the file aren't what is expected, it won't be able to be viewed or heard properly. For example, here are parts of 3 files: a .class file, which is a Java binary, a JPEG file, and an MP3 file. And this is the base 16 view rather than base 2. And we can see, for example, that the foo.class file begins with a special bit sequence that in hexadecimal spells Cafe Babe. All .class Java files begin with that same bit sequence. JPEG files all begin with the sequence FFD8FF. So any JPEG file will begin with that bit sequence. Here again we see the hexadecimal or base 16 version. Now MP3 files are somewhat more complicated. They don't apparently all begin with the same bit sequence, but we can see in the MP3 file strings shown on the right, so ID3 encoded by, gives some information about what's in these files. When you open a file, the viewer that you use will display it in a particular format. So for example, here is a JPEG file. We know it's JPEG because it begins with that bit sequence of FFD8FF. However, just looking at those bits in base 16, or if we did in base 2, we can't really see what's in the file. When we display it by using open, for example, on a Mac, or opening it with an image viewer on a Windows machine, we see that it's Picasso's Guernica. Now we might be able to tell that by the fact that the name of the file is guernica.jpg, but remember, the name doesn't tell us what's in the file. We have to look at the bits to determine that. This is Radia Perlman. She doesn't like to be called the mother of the internet, but some people have used that appellation for her. She's in the Internet Hall of Fame. She is an ACM fellow because she invented the spanning tree protocol used for routing on the internet today, as well as many other contributions to networking. She says, "Life is unfair. It drives me crazy because I want it to be fair. But obnoxious, backstabbing people do well for themselves, while really nice, deserving people don't do as well as they should. This will never change, and you have to not let it bother you too much. It's okay to ask for help," she says. "When doing a final exam, all the work must be yours. But in engineering, the point is to get the job done, and people are happy to help. Corollaries: you should be generous with credit, and you should be happy to help others." Woto personified. Thank you, Radia Perlman. Enjoy compression.